Hello, everyone. Welcome to today's presentation. In this video, I would like to introduce you ATR, a template-based repair tool for Alloy specifications. Alloy is a modeling language. It has been used to model many software-related problems. For example, it has been used to capture some IoT system security-related bugs. And it also has been used to model a surgical robot arms, which they capture some arm angle related security properties. And also it has been used to model the European railway system schedules so that there shouldn't be any crash happen. Unlike the imperative language like Java or C, Alloy is a declarative language. So there is no order of the statement and there is no control flow. All the statement in Alloy specification would be converted into a large logic formula, and then the backend solver would solve the formula and give some result. Alloy is pretty powerful. However, it lacks some automated tool support. So in this presentation, I would like to introduce you ATR, which will automatically repair violated assertions. It uses PMAX set to generate similar instances, and it uses some template-based repair techniques to generate repairs. So first, I would like to start with the security lab example. On the left hand, we could see an Alloy specification for this secure lab, in which what we would like to achieve in this Alloy model is a security property that only researcher can enter the secure lab. So in this Alloy model, we use SIGs to define some classes, like we define some rooms and one special room secure lab. And we also have some persons that work in this secure lab, and which are divided into two categories: the employees and the research. All of them will own some key. And also we have a SIG to define the key class, which opens certain room. And we also have some constraints that defined in the facts. For example, we would like to have at least one employee and at least one researcher, and all the employees have to own at least one key. And we want to see that all the rooms have to be opened by some key. And here we try to constrain the secure lab, the security property for the secure lab. So we see that all the employees, there exists some key that the employee owns this key, and this key cannot open the secure lab. And then we have this assertion trying to check whether our secure property is satisfied or not, which it says if a person can enter the security lab, then that person has to be a researcher. Then we have this check command. And when we run this check command, Alloy would convert this whole specification into a Boolean formula, and then it will use some backend solver to solve this large formula, and it gives this counterexample in which we can see the employee owns K1 that opens the secure lab. This shows that the assertion is violated. So there is something wrong with our Alloy specification. So for that example, it would be easy to find why the counterexample violates the assertion. But how about when we have more complicated Alloy specifications? For example, this is the counterexample provided by the Alloy for the surgical robot arm model, in which it becomes super complicated and it's hard for humans to manually analyze why this counterexample is a counterexample. So we developed ATR, which tries to automatically repair such kind of situations. It given some alloy specification, it first checks whether you have some counterexamples. And if you have some counterexamples, it will use the PMAX set to generate closely similar counterexamples and satisfying instance. And then it compares the counterexample and the satisfying instance to identify why the counterexample violates the assertion. And then it uses some fault localization and to locate some suspicious expressions. And then it generates some templates and generates some patch and then patch back to the original buggy alloy model and see if it fixes. If not, it will repeat the whole process. How would ATR work for this secure lab? So first, it identifies by comparing the counterexample and the closely similar satisfying instance, it first identify why the counterexample violates the assertion. It identifies that, in the counterexample, the employee owns K1 and K1 opens secure lab. How does ATR find this? It compares the difference between the counterexample and the satisfying instance. The problem now becomes, how do we find this perfect satisfying instance? The instance generation of alloy is random. This is because when alloy solves the backend alloy set solver, it's random. It generates arbitrary solutions for a Boolean formula. So how could we generate this expected satisfying instance? So in ATR, we convert the problem of this instance generation to a partial max set problem, in which the PMax set problem defines two kind of clauses. The first one is a hard clause and the second one is a soft clause. And the PMax set solver would try to find a solution that will try to satisfy all the hard clauses and satisfy as many soft clauses as possible. So in our case, we convert the counterexample to the soft clause and the original alloy specification as the hard clause. That the PMax set solver would give us a result, which is an instance that satisfies the asserted property and has minimal difference from the counterexample. So then we would try to, after ATR identifies the differences, ATR tries to generate expressions to capture this difference, which the expression that captures this difference would be a potential repair for the bug. And we try to use a subset of the alloy syntax that would be mostly used. So for example, we would have some 3 levels of templates. The first one would be the relational, which just generates some, use some relational operators like the connection and the union of set, those kind of relational operators to connect like the basic variables like the atoms, SIGs, and fields. After we have the relational template, we would then generate more complicated Boolean templates that basically connects all these relational templates with Boolean operators like equals, not in, and subset, and not subset. Finally, we would then connect those Boolean templates with logic operators to generate like something like if A in B, then it implies C in D. And we use this A not in B template generates the patch that E is not in opened by Secure Lab, that which generates a repair for our example of the Secure Lab example alloy specification. So to evaluate our technique, we conduct experiments that tries to answer 3 research questions. The first one is, can ATR repair alloy bug effectively? The second one is, what are some interesting characteristics of ATR repairs? And the third one is, how does ATR compare to other alloy repair techniques? We can collect two benchmarks from previous work. The first one contains 38 specifications from 12 alloy problems. It models some array binary search tree address book, which comes from some graduate student homework and also come together with the original alloy program. The second one contains 1936 specifications from the Alloy for Fun project, which contains 13 alloy jobs for students to complicate, like graphs classroom. We collect all the attempts for for all the students. And for RQ1, the performance of ATR, we can see that ATR repairs 308 specifications out of 1974 alloy specifications, which achieves 66.3% repair rate in using an average of 364 seconds. For RQ2, we analyze the repair characteristics of ATR in the following criteria. The first one is the similarity to ground truth. We use the syntax edit distance as our metrics, and the ATR shows generates repairs that is 5 edit distance to the ground truth. For example, in this one, the ATR generates the following repair where the oracle looks like this, and this shows that the ATR is 1 edit distance from the oracle by basically just changing S1 to state. And we also notice that ATR could also be used as a synthesis tool. In one example, it fills the empty predicate. For example, in the alloy specification, it has an empty predicate. This has at most 1 child for tree. And ATR actually fills this predicate with the following correct expression. And also we notice that there is also some overfitting repairs for ATR, which shouldn't exist for this assertion base, but this is due to the inaccurate fault localization. We actually try to manually provide ATR with the most accurate fault localization, and ATR actually solves these overfitting problems. And the third question is the third research question. We compare ATR with other alloy repair tools, and the state-of-the-art alloy repair tools are A-Repair and B-Affix. For ATR, it correctly generates repairs of 300 out of 1974 alloy specifications with a repair rate of almost 66%, with an average of 364 seconds. It compares to the correct repair rate of A-Repair of 9.8% with an average of 92 seconds. The reason why A-Repair generates such a low repair rate is because it generates 1500 for 1500 alloy specifications, it generates overfitting repairs. And for B-Affix, it has a repair rate of 50.9% with an average runtime of 70 seconds. We can see that ATR has a highest correct repair rate with a medium runtime. So in summary, we introduced ATR, which repairs violated alloy assertions. It used PMAX set solver to generate closely similar counterexamples and satisfying instance. It adopts the template-based repair techniques. And In our experiment, ATR has a 6.4% repair rate for 1947 alloy specifications with an average runtime of 364 seconds. You can download the ATR as its GitHub repo and with all the alloy specifications. Thanks.